In this video, we are going to talk about horizontal asymptotes. So we've already discussed vertical asymptotes, and this is the diagram that we did in the review portion of the last video when we talked about vertical asymptotes. So we're going to talk about horizontal asymptotes. So talking about the original reciprocal function, right? Did it have a horizontal asymptote? Well, yes, it did. At what value? At what value? Y equals what? Y equals 0 was our horizontal asymptote, which I'm going to draw right here, which we just know, and we knew that if it moved up or down, the asymptote moved with it. But today we're going to talk about Y. Y is Y equals 0, the horizontal asymptote. Well, let's look at this function. If I have Y equals 1 over X, right? And X gets infinitely larger. So X is getting bigger and bigger and bigger. So I get, right, if I have a table, let's do, oh, right. If I have X is equal to 1, it's 1 over 1, which is just 1. If I have X equals 2, it's 1 over 2. If I have 10, I have 1 over 10. If I have 100, I have 1 over 100. What is happening as X gets bigger? What is happening to Y? Well, Y is getting smaller and smaller and smaller, right? Because 1 over 100 is a lot smaller than one whole, right? I'd rather have a whole cookie than a 1/100th of a cookie, right? That's a crumb. I like having more like 100 cookies, especially in quarantine, but we're not going to talk about that. So it's really important here that we understand as X gets infinitely, infinitely bigger, Y is getting infinitely smaller, but will Y ever reach 0? If it's 1 over some number, will Y ever reach 0? No. 1 over something will never be 0, right? Even if we get to 1 over 1 million, that's still not 0. It's an extremely small number, but it is not equal to 0. So your function, as it gets infinitely bigger, will never reach 0, right? But then what happens when it gets infinitely smaller? So x is, let's say, x is -1. Well, we have 1 over -1, which is -1, right? So it's going to be somewhere like there. Then we have, let's say it's -2. Then we have -1 over 2. Then we have -10, -1 over 10, -100, negative. So it's the same behavior, right? But it's just in the negatives now. So as x is negative, y is negative, right? So, but now it's getting a smaller absolute value, but now it's negative. So it's getting closer and closer and closer and closer and closer to that horizontal asymptote, which is y equals 0. So it's getting closer and closer to 0, but it will never actually reach 0. So that is why we have this horizontal asymptote as y equals 0. The whole point of your horizontal asymptote, and I'm going to write this down because it's important, is we need to focus on the end behavior. Meaning, what happens as x gets infinitely larger, y approaches what number? So just a little recap of what we've done in the past when we did polynomial functions is we said as x approaches positive infinity, f of x approaches, and for polynomial functions, it was always positive or negative infinity, right? This was always the thing. But with this function, right, let's talk about it as if we're talking about this reciprocal function, right? As x approaches positive infinity right here, right? This is positive infinity. So as x approaches positive infinity, what does f of x approach? It's not going to positive infinity or negative infinity. No, the function is actually approaching f of x, or y is approaching 0. And as x approaches negative infinity, right, this way, as x gets more and more negative, f of x also approaches 0. So it's always, for a horizontal asymptote, it will be the same thing. These will be the same. But It's really important that we understand that horizontal asymptotes have to do with end behavior. What that also means is that, and I'm gonna oh, I wrote this down here. All right, we'll talk about it in a second, but let's just review what a rational function is. A rational function P and Q are polynomials with no common factors other than one. The graph of a rational function is this where, now, I said that it was important. The last video I explained the degree of P of x and Q of x are important. So the degree of P of x is m, and the degree of Q of x is n. Okay, let's make that smaller. So we have m and n. So whatever P is, so let's say I have x squared over x plus 1, m is equal to the degree of P of x, which is 2, and n is equal to 1. The degree of this is 1. So really, really valuable things to understand because it's really going to come in handy later on. So horizontal asymptotes, just some notes that I wrote out. So has everything, oh, let's make this thicker again, has everything to do with end behavior, okay? When we did end behavior of polynomials, we only looked at the first term of the polynomial because it was the only thing that dictated the end behavior. So let's talk about that because I'm sure all of you are complete geniuses of end behavior still from the polynomial unit, but in case there's that one or two of you who's not, I'm gonna explain it. So remember when we did end behavior, so if I had a polynomial like negative 2x to the fifth plus, or let's just do 2x to the fifth plus 3x plus 5. I'm not even gonna write out all the terms. This was the only term that was important when we talked about end behavior. So we looked at the coefficient and we looked at the degree. The degree was odd, so I knew it went in opposite directions, and it was positive, so it looked like a positive slope. Unlike if it was a negative 2 in front, it still would have went in opposite directions because it's an odd degree, but it went like that. So what's important here is that with polynomials, because we are dealing with polynomials, remember that with polynomials, the only thing that's really important here is the first term, because the degree of the first term pretty much outweighs all of the other terms that have lesser degrees. So that's what we're going to be focusing on. So in the same way, the first terms of P of x and Q of x are all that matter when we are talking about the end behavior of rational functions. Okay, so there's also, I didn't write this down, but I want to make sure we understand one thing. Because end behavior has everything to do with, horizontal asymptotes have everything to do with end behavior, it's important to note that the function may cross the horizontal asymptote. This is what makes it, so this is unlike vertical asymptotes. The function may cross the horizontal asymptote because if I have something like this and the function goes like this, right? There are two vertical asymptotes. And so this might look like this in the middle, and it might look like this at the end, right? See, notice how there are still x-intercepts, or there's still a point where it crosses the horizontal asymptote. But what's important, again, is the end behavior. What is happening at infinity, not what is happening in the middle. So the middle is not important. It's what is happening in the ends. What is it infinitely approaching? Now, also what may be different from horizontal asymptotes versus vertical asymptotes is that there is at most one horizontal asymptote. There can be none, but there can be at most one. So you're either going to have none or one. Okay, and we're going to talk about how to find what it is. So let's do some problems. These are the exact same functions that we worked with in the last one. But notice how I didn't factor it because it's not important. What's important here is the first terms, boom and boom. Because when we are dealing with infinity, right? When I'm dealing with 2 times 1 million minus 8 over 1 million squared minus 9, these minus 8 and minus 9 are literally so insignificant, right? If I'm a millionaire and I lose $8, it makes no difference in my life. But if I'm me and I lose $8, I cry about it. So I'm not a millionaire. But the point is that all of these following terms are not important when we're dealing with infinity, because infinity is really, really, really large or really, really, really small numbers. So it's really important to understand that so it's kind of like the supporting roles. Like, yes, they're valuable, but right now, when it comes to the end product, they're not important right now. Just kidding. Supporting roles are really important. So 2 times a million. So let's talk about the behavior as it's getting bigger, right? 2 times a million minus 8, and then a million squared minus 9. Which one is going to be bigger? Well, this right here on the bottom is definitely going to be bigger than this, right? 2 times a million is 2 million. 2 mil minus 8. 1 million squared is, oh God, I don't even know. Let's find out. 1 million squared. See, Desmos doesn't even want to tell me. They just know it has 12 zeros. So that's like 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Sounds like I'm doing like Zumba. Or dancing. 1, 2, 3, 4, 5. Anyways, minus 9. Which one's bigger? I think this one. So the point is here is as x for this function right here, as x is getting infinitely larger, what is growing at a quicker rate? The numerator or the denominator? Well, the denominator for this problem, the denominator is growing at a quicker rate. What is that? At a quicker rate. So therefore, what? What is it approaching? What number is this approaching as it gets infinitely and infinitely closer to 0? It's infinitely larger. It's approaching, so the number is getting smaller. So as x grows, the function, so f of x, or g of x for this one, g of x, what's the opposite of grows? Or I'll say as x increases, g of x decreases and gets closer and closer to what value? If it's decreasing infinitely, it is getting closer and closer to 0. So my horizontal asymptote is what? Y equals the same as the reciprocal function, y equals 0. So conclusion, if the degree of, p of x is greater, is less than, so the numerator, I'll actually write it like this. If the degree of the numerator is less than the degree of the denominator, then my horizontal asymptote, therefore, that's a therefore symbol, y equals 0 is my horizontal asymptote. Okay, so let's look at a different problem. Like this one, right? We did this problem. Now what I did was I figured out what my leading coefficient, my leading term was going to be. So I know x squared times x times x times x is x to the 5th, right? Again, all of these do not matter for end behavior, okay? For everything else it matters, but for this, it does not matter. So, and then I have 20 times x times x times x, which is 20x cubed, and here we had x squared, x, and x, which is x to the 5th. So let's look at what my end behavior is going to be. As x gets infinitely and infinitely bigger, I have x to the fifth, and then I have 20x to the third. Which one is going to grow at a faster rate? My numerator. My numerator is going to grow at a faster rate. Therefore, if I have a number like a million to the fifth power is a gigundo number, and then 20 times a million to the third power. This 20 is just multiplication. It can't beat the 1 million to the fifth. So the coefficient doesn't define how quick it grows. The degree does. So if the numerator is getting bigger at a quicker rate than the denominator, then that means that this function, as x grows or increases, what happens to f of x? It also increases because, again, the numerator is growing at a faster rate. So that means that if I have like 10 over 2 and then I have 20 over 3, right? This is growing, but it's not growing as quick as this. And then if I have 40 over 4, right? This was a 5, and now this is a 10. So it's growing, even though both are growing, if the numerator is growing at a faster rate, the function is growing also. So that means that there is no horizontal asymptote, right? Because as one approaches infinity, the other approaches infinity. So no horizontal asymptote. It just approaches infinity. Oh, I forgot to show you guys on decimals what it looks like. So let's look at that one. This is it. So look at it. So notice it crosses the function, it crosses everything, right? But there's no horizontal asymptote. The reason we know that is because, look, as x gets bigger and bigger and bigger, the function just goes off into outer space. This one too. As it gets lesser, as it decreases, it goes off into outer space. Let's look at the first function we did. As x approaches positive infinity, right? This was the first function when the denominator had a higher degree than the numerator. It still crosses x equals 0 at 4, but it swoops right back down and starts approaching 0. And look at over here, it also still approaches 0. Okay, let's look at one more, our last case scenario. So we already looked at if, so let me write this here. If the degree of the numerator is greater than the degree of the denominator, then you have no horizontal asymptote. So we looked at if the degree is numerator is greater. We looked at if the degree of the numerator is less than. So what's the last case scenario? Well, what happens when the degree of the numerator, so I'll write this here, the degree of the numerator is equal to the degree of the denominator? Well, which one is going to grow at a faster rate? So at the beginning, this one is technically going to grow at a faster rate, right? Because it's doubled, right? Or honestly, at the end of the day, right, none of these matter, right? We spoke about that like 50,000 times. None of those matter for end behavior. But so I have 2x squared plus blah, blah, blah over x squared plus blah, blah, blah. So as we get bigger and bigger and bigger and bigger, right? And I put a million, or let's say I put 100, right? I put 100 in and I get 2 times 100 squared, and this is just 100 squared. They're both growing at the same rate, right? This will be 100 squared, 1,000 squared, a million squared. This will also be 100 squared, 1,000 squared, a million squared. But what will the numerator always be, or what will it always have on top of the denominator? Well, this 2 means that the numerator will always be double the denominator, right? So as this gets infinitely and infinitely larger, the actual growth rate doesn't matter because they're the same, but that 2 is important. So if I have 2x squared over x squared and I simplified this, I would get what? 2 over 1. And so therefore, my asymptote is going to be 2. So this is where it's important. So the degree of the numerator equals the degree of the denominator. Then, therefore, the horizontal asymptote is your leading coefficient of the numerator over the leading coefficient of the denominator. So just a little thing. If I had 3x to the fourth plus blah, blah, blah over 2x to the fourth plus blah, 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 my horizontal asymptote would be y equals 3 over 2 because these cancel out. But the numbers don't. So again, recap. If I have anything, I have to take my first terms and pretty much simplify them and see what happens. So for this one, I could have taken this and said, okay, x to the fifth over 20x to the third. If I simplify this, this is x squared. So it becomes 1/20th x squared. And this is just a polynomial. The end behavior is positive to positive. As one gets higher, the other gets higher. This one, if I simplified 2x over x squared, this cancels out and I get an x on the bottom. So I get 2 over x. We're back to our reciprocal function. As one increases, the other decreases. So it goes to 0. So here I have the in general. I'm just going to leave this on the screen. If you want to take a picture of it, you can. I'll also put it in the comments. Not the comments, the Edpuzzle.